Hello everyone, welcome to my channel. Today I am going to solve one chemical process calculation problem. Here is the problem statement. A chemical plant produces methanol by the reaction of carbon monoxide plus 2H2 that will produce methanol CH3OH. The fresh feed contain carbon monoxide and hydrogen in stoichiometric ratio. The recycled stream containing 5% methanol, 15% carbon monoxide and 80% hydrogen by moles is mixed with fresh feed. The reactor achieves 80% conversion of carbon monoxide per pass. The product stream from reactor is sent to a separator where 98% of methanol is recovered as product and the remaining stream is recycled. Determine the fresh feed rate, recycle rate and methanol production rate for the producing 1000 kg per hour of methanol. Now in that slide flowchart is already given. Now here methanol synthesis process already we know that is carbon monoxide and hydrogen that is produced the methanol. The goal is to determine the required fresh feed rate and recycle rate as well as methanol production rate to consistently produce 1000 kilogram per hour of methanol. So we are given several key details. The fresh feed contains carbon monoxide and hydrogen in a stoichiometric ratio of 1:2. The reactor achieves 80% conversion of carbon monoxide per pass. The separator is highly efficient, recovering 98% of methanol as the final product. The recycled stream contains 5% methanol, 15% carbon monoxide and 80% hydrogen by moles. Now already I told you that the simple flow diagram of the process is already given uh, in that slide. The fresh feed enter the mixture. Here you can see that where it combines with recycled stream. This combined stream then flows into the reactor where the conversion takes place. The output from the reactor is sent to the separator where the product methanol is largely recovered and the remaining stream which contains unreacted gas some methanol is sent back as the recycled stream to the mixture. The recycle loop is key to improving the overall process efficiency. Now before we begin the calculation, let's look at the given data, particularly the molecular weight. The molecular weight of carbon monoxide that is 28 gram per mole, hydrogen 2 gram per mole and methanol CH3OH that is 30 gram per mole. The target production is here 1000 kilogram per hour of methanol. So first here we convert this mass flow rate into molar flow rate, which is more convenient for the reaction balance. So here methanol production rate that is 1000 kg per hour into 1000 gram per hour, 1000 into 1000 gram per hour, okay, divided by 32 gram per mole. First we have to convert to kg to gram and then divided by 32 gram per mole. So we'll get the total mole that will the target production of methanol, that is 31.31250 mole per hour. That is the target production rate. Separator material balance. We start by performing a material balance around the separator. So here CH3OH balance around the separator. We know that the separator recovers 98% of methanol entering it and the product stream is 31.250 mole per hour. So we can find the total mole methanol entering the separator, which is amount produced by the reactor. So methanol entering separator, that is product by recovery efficiency, that is 31250 divided by 0.98. So that is 31,887.8 mole per hour. And the amount of methanol that is not recovered, the remaining 2% leaves into the recycle stream. So here methanol in recycle, that is equal to methanol entering minus product rate, that is methanol entering is 31,887.8 minus methanol product is 31.250. So that is 637.8 mole per hour. Now here total recycle rate. So we are given that recycle stream is 5% methanol by moles. So total recycle rate will be methanol in recycle divided by molar fraction of methanol. So that is 637.8 mole per hour divided by 0.05, that is 12.756 mole per hour. So total recycle rate is 12,756 mole per hour. Now here recycle steam components. So now that we know the total recycle rate is 12,756 mole per hour, we can calculate the flow rate of other component using the given molar fraction. So carbon dioxide in recycle, that is given 15%. So we can multiply that is 12,756 into 0.15, that is 1913.4 mole per hour. And hydrogen recycle is 12,000, that is given is 80%. Okay, so 80% in the recycle stream. So we can calculate easily. So that is 12,756 into 0.80, that is 10,204.8 mole per hour. And we already know that the recycle of methanol, that is 637.8 mole per hour. So total is 12,756 mole per hour. So in that the right hand side, that flow diagram is already given. So separate 98% methanol recovery, and react from the reactor mix product is coming. So that is 31,887.8 mole per hour is methanol plus unreacted carbon dioxide and hydrogen, and 98% recovery means 1000 kg per hour methanol is produced. A recycle stream, we know all this information. Now here reactor material balance. Now we move to the material balance around the reactor. So that is methanol production first, that is CH3OH produced in the reactor, that is 31,887.8 mole per hour, uh, that we know from the previous slide. So CO conversion, carbon monoxide conversion, since reaction is there, carbon monoxide plus 2H2, so that is methanol. The stoichiometry ratio is here 1:1. So CH3OH produced 1 mole of CH3OH produced, that is 1 mole of carbon monoxide is consumed, right? So CO converted in the reactor is CH3OH produced, so that is 31,887.8 mole per hour. And now here in that problem, so 80% conversion of carbon monoxide per pass. So CO entering the reactor 31.887.8 divided by 0.80, that is 39,859.75 mole per hour. So next is mixture material balance. So the carbon monoxide entering the reactor must equal to the carbon monoxide in the fresh feed plus carbon monoxide in the recycle stream. So that we know. So carbon monoxide entering reactor is equal to fresh carbon monoxide plus recycled carbon monoxide. So we already know that carbon monoxide entering the reactor, that is 39,859.75 is equal to fresh carbon monoxide. So that is we don't know, but recycled carbon monoxide we know 100913.4. So fresh carbon monoxide is 37.946.35 mole per hour. Now from here we can easily calculate the hydrogen balance, that is stoichiometric phase speed. The problem states that the phase speed contain carbon monoxide and hydrogen in a stoichiometric rate. So that is 1:2, means 1:2 ratio. So fresh hydrogen will be 2 into fresh carbon monoxide. So that will be 2 into 37,946.35. So that is 75.892.7 mole per hour. So total fresh feed will be carbon monoxide plus hydrogen rates. So total fresh feed will be 37,946.35 plus 75,892.7. So that is 113,839 mole per hour. So here is the complete flowchart. So whatever we calculated, so that values are given here in the flowchart. The mass balance in kg per hour. So we got all this flow rate in moles per hour. So now we can convert this fresh feed rate into the required units of kilogram per hour. So fresh feed rate that is fresh carbon monoxide, that is 37946 mole per hour. So we can multiply it with 28 gram per mole, so that will be 1062.5 kg per hour. Similarly hydrogen, so we have 75893 mole per hour flow rate, so multiply it with 2 molecular weight 2 gram per mole, so that will be uh, we can do that, multiply and then divided by 1000, so we'll get 151.8 kg per hour. So total fresh speed will be 1214.3 kg per hour, and product we already know, that is 1000 kg per hour. Now here overall process balance, so input, so fresh speed only, so that is carbon monoxide 37,946.35 mole per hour, hydrogen 75,892.7 mole per hour, output product only, so that is CH3OH, that is 31,250 mole per hour. So now here we can check the consumption. So carbon monoxide consumed is equal to CH3OH produced, so that is 31 according to stoichiometry. From we can easily get from this that reaction stoichiometry, so that is 31,250 mole per hour. H2 consume 2 into CH3OH produced, that is 62,500 mole per hour, and H2 excess is 75,892.7 minus 62,500, that is equal to 13,392.7 mole per hour, so that is recycle. Now here single pass conversion, so that is already know, that is given in that problem, the 80%. Now overall conversion, that is 82.3%. Now here carbon, if I do the atom balance, so that is 37 946.35 mole of carbon in and 31,250 mole carbon out, so conversion is 82.3%, and so remaining carbon in unreacted carbon monoxide, that is in recycle. And hydrogen, so that is 151,785.4 mole hydrogen in and 125,000 mole of H out, so that is again 82.3% conversion. So total is total overall conversion is 82.3%, and recycle ratio, so we can calculate that, so 12,756 by 113.839, okay, so that is 0.112. And CH3OH recovery, so that is already given, so that is 98%. So summary of the result, so fresh feed 113.839 mole per hour, so that is 1,214.3 kg per hour. Fresh carbon monoxide, that is 1,062.5 kg per hour. Fresh hydrogen 151.8 kg per hour, right? And recycle rate, so that is 12,756 mole per hour, and overall conversion is 52.3%, and process efficiency high due to effective recycle stream. So that's it for this problem. Thank you.